Good morning, everyone. Welcome back to Organic Chemistry 1 here this summer. Um, I know that you guys just recently took a test, but at the time of this recording, many of you still haven't taken the test yet, so I can't really discuss the test yet until everyone's taken it. That being said, I've decided that I'm going to go ahead and once everybody's taken the test, I'll make a video going over the entire exam and also your quizzes too. I thought that might be helpful for you to study during the for the final exam. So we're going to go ahead and get started with our first lecture for the week, and it's going to be about acids and bases, one of my favorite topics in chemistry. But it's got a organic twist on it because you've already gone through quite literally chapters on acids and bases back in back in general chemistry. But now we're going to have a little organic twist on the acids and bases. So let's go ahead and get started. So in general chemistry, we had a couple different theories when it came to acid-base theory. Actually, there are three, I think, that they covered in general chemistry. The first one was actually called the Arrhenius acid-base theory. It's not mentioned here, but I just wanted to remind you. Can't even remember how to spell Arrhenius. Down in the comments, someone tell me how to spell Arrhenius. I can't remember. Arrhenius. That doesn't look right at all. But that's the Arrhenius acid-base theory. And in Arrhenius acid-base theory, if you recall from Gen Chem, an acid donates a proton, or an H plus, to the solution, and a base donates a hydroxide to a solution, to water, right? And that was the Arrhenius acid-base theory. The problem with the Arrhenius acid-base theory was that it was so confining, right? And so strict. It only allowed for protons and hydroxides, but we know now that there are plenty of other different bases and acids, or plenty of other species that can be involved, rather, when we're talking about acid-base chemistry. And by the way, when I say the word species, I mean like ions or polyatomic ions or things like that. That's a species, right? So chemists came up with a more broad definition of acid bases. It was called the Bronsted-Lowry acid-base theory, right? And so my old teacher used to actually call it BLAP. BLABT, BLAPT, right? Because you could put at the end there theory, right? Put at the end theory, and now it's Bronsted-Lowry acid-base theory, and it's BLAP. And that's how we would remember what Bronsted-Lowry acid-base theory was, BLAP, right? And in Bronsted-Lowry acid-base theory, the definition is that an acid actually donates a proton, right? Just like in Arrhenius acid-base theory. But in Bronsted-Lowry acid-base theory, a base accepts a proton instead of donating a hydroxide, because there are a lot of things that could be bases and can accept protons, right? So, if you recall from general chemistry, like I was saying, this example here, right? The acid is the proton donor, and the base is the proton acceptor. Okay, the base is the proton acceptor, and the thing about it is that you can actually see some electron pushing occurring here, because, and I have to remind you of the electron pushing because we've been doing it in the couple previous lectures for resonance, right? Because a lot of the reactions that we'll be going over will be acid-base type of reactions, and so you have to know your electron pushing, right? So in this case, it will be the electrons right here from the oxygen that come over and take that proton, okay? And then the bond between the hydrogen and the chlorine from hydrochloric acid goes to the chlorine. And so that's why chlorine now has, chloride rather. That's why chloride now has a negative charge, And we have this here, which is a positively charged oxygen with three protons around it, and we call that a hydronium. Hydronium. That's the hydronium ion, right? And you're going to see a lot of hydronium ions uh, in the upcoming lectures, and in today's lecture too. And I have a sneaking suspicion that the next slides are going to be saying all the things I just said here, but it's going to repeat me again because I never know what's on the next slide. So let's go ahead and go to the next slide. Oh, okay, that's good. That's actually a good thing. So in Brownstein-Lowry's definition, right, of acid and bases, right, an acid will produce an acid will produce a conjugate base, right, and a base will produce a conjugate acid, right. And so in this case here, we have this species here, and we have a water, okay. And in this case, the water doesn't act like an acid. It's actually going to be sorry, the water does act like an acid. The other thing acts like a base, right? What is this? Tert butyl alcohol, maybe? 1, 2, 3, 4. Yeah, I think that's a tert butyl alcohol. Tert butyl alcohol. All right, tert butyl alcohol. I'm pretty sure that's what the name of that is. And so in this case, the stronger base here, sorry, the stronger acid here is the water, right? If you recall in the previous slide, the stronger acid, the thing that was donating the proton, was actually the hydrochloric acid, and water acted like the base. But in this particular in this particular reaction, water is actually going to act like the acid because it's the stronger acid compared to this tert butyl alcohol, which kind of makes sense. We'll talk about why that is in a second, right? So in this case, the electrons from the tert butyl alcohol will come over, pull off this proton from the water, and the bonds from the electrons from the bond in the water go to the oxygen, and so you're left with the tert butyl alcohol and the hydroxide ion, right? So we would identify this then being the acid, right? And this over here being its conjugate base. And then over here, the tert butyl, or I guess it would be not a tert butyl on its own because it doesn't have the hydrogen yet. It would be like a tert butoxide, right? Tert butoxide. That becomes a tert butyl when it takes that proton from water. And so then, since this is the one that's receiving the proton, this is the base. And then on the other side of the reaction, it's called the conjugate acid. Conjugate acid. Right? Oh, sorry, I didn't realize my head was blocking this over here. So the hydroxide ion over here is referred to as the conjugate base. Okay, conjugate base. So remember, an acid yields a conjugate base, right, over here, and then a base yields a conjugate acid over here. And then one of the things that you can always remember is that the acid yielding a conjugate base always ends up with a negative species, right, an anion, right, which makes sense because it just lost a proton. So if you lose one proton, which is a plus charge, right, then you're going to be negatively charged. And then the base becoming the conjugate acid over here, right, you're going from being a negative charge to being neutral now, right? Cool stuff, cool stuff. So I kind of skipped ahead, right? But here it goes talking about how to use use what we learned in resonance structures with moving electrons around with arrows, right? And we can do that with acid-base chemistry as well. We can do that with all chemistry, actually, but we'll slowly make it up to that. Okay. So here we have a generic base, and this generic base has a lone pair of electrons, right there. And I shouldn't draw an arrow there because it just confuses people. But here we go. There we go. The lone pair of electrons. And that lone pair of electrons really likes that proton from that acid right there, right? So it's going to come over and take this proton away. Okay? And then when it does that, this bond here that was holding that H, that hydrogen, that proton to the acid, goes to the acid, right? Yielding you your conjugate base here, right? This is your CB for conjugate base, right? And then your conjugate acid over here, right? And of course, this is the base. It's already initialed that way, so you should know that that's the base and that's the acid. And just a reminder, right? Just a reminder, the acid always yields the conjugate base, right? And then the base always yields the conjugate acid, right? So the thing I just want you to remember, though, is that the curved arrows are actually describing the physical movement of electrons, right? That's really, really important. So you have to learn how to draw mechanisms. It is one of the most valuable skills in this class, okay? And just remember, in the very first lecture I told you, right, that pushing electrons and drawing the movement of electrons in a molecule and from one molecule to another is a simple thing once you get the hang of it, because all you do is you move electrons from the more negative thing to the more positive thing, right? Or electrons go toward electron sinks, right? And in this case, you have a lone pair of electrons on this base right here, right? On this base right there. And what is it attracted to? It's attracted to this positively charged proton right here, right? It's attracted to that positively charged proton. That's why it takes it. Okay? Make sense? And then knowing that kind of thing, you can then start predicting reactions, right? It gets more complicated than that, but we'll get to there. We'll get there. So the previous slide with the acetate ion and acetic acid was a one-step acid-base reaction. So here we do a multi-step acid-base reaction, okay? So here we have, again, a this is actually tert-butyl alcohol, right? So some people abbreviate tert. Tert means tertiary, because that's a tertiary carbon in the center, right? It has 4 things attached to it, and tert is 4 in Greek, or maybe it's Latin. Maybe down in the comments below, tell me if tert is a Greek word or a Latin word. I can't remember, but it means 4. Okay, and it means 4 things are attached to that carbon right there. 4 substituents, right? Not just hydrogens. And so a lot of people abbreviate tert-butyl as T-butyl alcohol. Can't even spell alcohol. Alcohol. I spelled it wrong in the previous slide, I think. I spelled it without the L at the beginning. Oh well. Okay. So in this case, what's happening is that the electrons that are on the oxygen of the alcohol, of the tert-butyl alcohol, right, is going to attack the hydronium ion here, right? Because the hydronium ion can act as an acid. And so when that happens, the bond between the oxygen and the hydrogen on the hydronium ion breaks, and it gives you your tert-butyl alcohol, right, with an extra proton attached right there, right? And that's why it's positively charged, okay? That's why it's positively charged. Remember that an oxygen with 3 bonds to it and 1 lone pair is missing 1 electron, right? So that means it's positively charged. After that happens, right, the bond between the oxygen and this tertiary carbon breaks, okay? And what's interesting about that is that you end up with water, right, coming off as a leaving group, right? And the cool thing though is that you have two waters being made. It's not reflected here; it just says H2O, right? But you have the water that was from here, that was made from when you pulled off the proton off the hydronium ion, right? So that's number one. That's water number one. And then water two comes from when the water comes off of the tert-butyl oxide, the tert-butyl alcohol, right? And so when that happens, we're left with a positive carbocation sitting right there, okay? And then now water can act as a base now and pull off the proton, right, from the methyl group that was at the end there, right, from the methyl group at the end there, okay? And the reason why I can do that is because the electrons from the proton there can now go and form a double bond to satisfy this carbocation right here, leaving you with an alkene, right? Now that was a little bit complicated. It's probably one of the largest. That's probably the largest reaction that we've gone through ever in this class. So don't worry, it'll get a little bit easier. Okay. So before, I love how the textbook says these kinds of things. Before long, you will be drawing mechanisms like this one. Yeah, because that one was a little bit. For now, just worry about correctly using the curved arrow to show the acid-base interactions, like the proton transfers, right? So there is a proton transfer there. Okay. This right here, this part right here, the second step was not a proton transfer, so don't worry about that so much. But this is a proton transfer here, right? That's a proton transfer there. And it didn't even show this, but once you pull out that proton, right, you actually get out of it the hydronium ion again. Right? You get out of it the hydronium ion again. So you started with the hydronium ion, and then you came out of it with the hydronium ion. Cool stuff, cool stuff. I guess technically it did show you that there were two waters here, because there's one water there and there's one water there. But, you know. So, Skill Builder 3.1, drawing mechanisms of a proton transfer on Wiley Plus. Make sure you look that up. All right? Make sure you look that up. Let's keep on trucking. Again, I understand that was a semi-complicated reaction mechanism with electron pushing for what we're doing at this point in the class, but don't worry, before the end of the semester, you'll get super good at it. Just focus on, for now, like they say, just focus on the electron transfer, the proton transfers. So now that we've gone through and explored, briefly how to move electrons around and protons around in structurally in acid-base chemistry, we can then now talk about something that you've talked about before in general chemistry, which is the relative strengths of acids and bases, or the relative weaknesses of acids and bases, right? And so there are a couple ways we can evaluate those strengths and weaknesses, right? There's the quantitative way, where we can use the pKa value to compare the strength of acids, right? Or we can do it the qualitative way, right? Where we can compare using the general stability of the structures. So quantitative quite literally means with the numbers, right? And then qualitative means what it looks like, right? What it looks like. So I'll give you a really good example of this. So I was saying before I was a forensic chemist, right? And so in drug chemistry, when we're testing drugs, for example, say marijuana, for example, right? There are several different tests you can use to do a confirmation test or a presumptive test and a confirmation test for marijuana. And so a couple of things you can do for qualitatively telling that it actually is marijuana and not something else, right? That's a qualitative test, right? Is you can do a couple things. There's this test called a Duke-Levine test, right, which is a color test for marijuana. But then the other thing that they do that's actually much more prevalent these days is that they'll look at the microscope, look at the marijuana under the microscope, right? And marijuana at the microscopic level has these like things called bear claws. They're literally called bear claws, right? And if they have those bear claws, which are actually called, I think they're referred to as syphilis hairs, right? And they look like bear claws. That's actually a qualitative test that a forensic lab does to uh, qualitatively test for the presence of marijuana, right? And then so that was the presumption test. I think this presumption means I think this is marijuana. Let me do something really quick to see if it is marijuana. So that's why you look at it under the microscope and you see the bear claws and you're like, okay, presumptively, qualitatively, it's marijuana. But the second part of that is that you have to do a confirmation test, something confirming what your presumption was. And generally, what we do is we use GCMS, and GCMS will stands for grass. I was just mowing the lawn. That's why it's on my mind. Anyway, gas chromatography mass spectrometry, right? And we'll get to that in way detail later on in the semester. Maybe even I think you'll really dive deep into it in organic too, what GCMS is. But I used to use GCMS a lot, right, as a forensic chemist, and there are actually marijuana has chemicals in it that make that make people high, THC being one of them, right? And you can actually detect that, and along with a bunch of other chemicals that are in marijuana, on the GCMS once it goes through and does chromatography and gives you a mass spectrum. And so the mass spectrum is the confirmatory test of the of having marijuana present in a sample. So the interesting thing is that is all qualitative. It sounds like quantitative, but it's all qualitative. What quantitative means is that they tell you how much is there, right? How much marijuana is there, or how much THC is there, not the marijuana itself, but the THC, because THC is the thing that people are going after here, like for example in court and stuff, right? And so to be able to do a quantitative analysis on the THC, that would be a quantitative test, and then you'd have to figure out what its concentration is, which most labs, and most jurisdictions don't really care about the actual concentration of the THC in the marijuana or the sample. They just care about the presence of it, right? And really, they care about the presence of it in a visually consistent sample. And so they're actually in the law, they're like not benchmarks, but like they're like thresholds of weights that will dictate how much weed or marijuana a person has and what charge that goes to, right? And it doesn't say in there what the concentration of the THC is. It says in there how much visually consistent material that has the presence of THC. So that is the difference between doing a qualitative analysis and a quantitative analysis. A quantitative analysis literally means by the numbers, a concentration of something, whereas a qualitative analysis is like the presence of something, what it looks like, right? So, good times in the drug chemistry. I was just going to say also that my girlfriend, she's actually a drug chemist and like in a forensic lab, and she knows way more about this stuff than I do. So maybe sometime I'll have her guest speak or something if you guys are interested in drug chemistry or something like that. Anyway, let's keep on moving. So, quantifying acidity using the Ka. You remember what Ka is from general chemistry, right? Ka is equivalent to the KEQ, right? The equilibrium constant of a reaction, but it specifically deals with the equilibrium constant of an acid-base reaction, right? So, if you have an acid and you dissolve it in water, right, you get the conjugate base and the conjugate acid, right? So you can write the KEQ equation such that you have the products right here, products. That's a B there for something. The products, right, over the reactants. And literally, it's the concentration of the products divided by the concentration of the reactants gives you the equilibrium constant, right? And so that can be translated to Ka, right? And Ka, since what we're worried about right now is the strength of an acid, right? Ka equals then the hydronium ion concentration times the conjugate base concentration divided by the acid's concentration, right? We're not so worried about the water anymore in the Ka because, um, you know, we're worried about the hydronium ion, right? This is the acid-base stuff, okay? The acid-base stuff. Because the hydronium ion is what accounts for the water, right? And the hydronium ion can act as an acid, okay? So the question then is that if an acid is strong, will the Ka be bigger than 1 or smaller than 1? Right? Bigger than 1 or smaller than 1? Well, let's think about this for a second, right? A strong acid means then that the ions of that acid dissociate, like let's say completely, right? So an example of that would be like sulfuric acid, okay? So sulfuric acid is a really, really strong acid. And so when you write out the KQ equation for sulfuric acid, or the Ka equation for sulfuric acid, you put the sulfuric acid unionized down here at the bottom, H2SO4, right? And then you put the ionized version, which is the sulfate ion, and the H3O up here. I kind of wrote it backwards there, but it doesn't matter, right? Remember order of operations, multiplication, it doesn't matter, right? So, since it's such a strong acid, most of it will actually become what? The sulfate ion, which means the number up here, right, will be very big. Okay? The number up here will be very, very big. And so very little of it stays as sulfuric acid, the unionized version, right? The unionized version. Let me just remove my head real quick so you can see that all I did there was write H2SO4 in parentheses, in brackets there, right? So what that means then is that the number of a strong acid, right, will be much bigger than 1. Okay? Much bigger than 1. But say you have the opposite, right? If you have the opposite, then most of the stuff that's unionized, say a good example of a weak acid would be like acetic acid, would stay that way, right? Would stay in the numerator as unionized, okay? And then up here in the numerator where the ionized stuff is, that number would be really small. So you would have a small number divided by a large number, and that would give you a very small number, smaller than 1, right? And that would be a weak acid, right? So generally, strong acids are bigger than 1. And then weak acids are smaller than 1, right? But you'll see in a second why there's a big problem with that. So you can see here that Ka values actually range from the the 10 to the negative 50s, which is way smaller than 1, right, to 10 to the 10s, right? Remember that this is the weak acids, and this is the strong acids, right? The stronger the acid, the bigger the number. The weaker the acid, the smaller the number. And in this case, the weak acids are way below 1, just like I said in the previous slide, right? Well, those numbers are really big or very small, so they're really difficult to work with, right? So as chemists, what we do is we take the negative log of the Ka, right? And when you do that, it focuses the range down from the 10 to the negative 50 to 10 to the 10 to negative 10 to 50, right? Negative 10 to 50. So quite literally, we're just taking the negative log right, of the entire Ka equation, right? So it's actually either this or this, but not both at the same time. Okay? And so now it's the pKa equals the negative log of the Ka. And when we do that, like I said before, the values now become between negative 10 to 50. And since it is the negative log, the lower pKa's actually denote a stronger acid, and the higher pKa's indicate a weaker acid. Okay. So let's take a gander here at this little table. It's not a big little table; it's actually a big table that spans 2 slides. But right, this is some pKa values of some common acids, right? And common compounds and stuff like that. And I was saying before, sulfuric acid, hey man, it's at the top right there, right? It's the strongest acid on this chart, and its pKa is -9, right? So again, each pKa unit actually represents an order of magnitude or power of 10. Okay? That means then, for example, sulfuric acid, right, with a pKa of -9, right, is 100 times stronger than hydrochloric acid at -7. Which makes sense, right? Because if we're talking about orders of magnitude or powers of 10, how many units is between hydrochloric acid and sulfuric acid, right? There's 2. From here to here, there's 2 pKa units, right? There are 2 pKa units, which means there are 2 zeros, because every power of 10 means a 0, right? And therefore, sulfuric acid is 100 times stronger than hydrochloric acid. Good stuff, right? I was talking before about the hydronium ion. See, the hydronium ion is a very strong acid as well, right? With a -7.4 right there. Oh, here we go. There's acetic acid. I was talking about acetic acid before. This is its conjugate base, right? Acetate ion. And it's got a pKa of 4.7, right? We'll just say 5 to make it easy. Okay. How many zeros is between 9? Sorry, let's say it this way. How many pKa units are between sulfuric acid and acetic acid? Okay, so that's a -9, so that's 9 already, plus 5, right? So that's 14, right? So that's how many? Wow, 14 zeros. What is that? 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we'll just do the little every 3 so we know how many millions this is, or quintillions. Okay, so I think that's right, okay? So that's thousands. Alright? Wait, so hold on. Okay, 100,000s there, okay? And then 100 million, 100 billion, and then 100 trillion. So, correct me if I'm wrong in the comments below if I'm wrong about this really huge number here, right? But I think that's 1 trillion. I may have counted my zeros wrong, but I think it's 1 trillion. Sorry, I'm a little hard of math, because I'm Asian and all. Anyway, if I'm right and that's trillion, holy crap, right? Sulfuric acid is 1 trillion size. Wow, 1 trillion. Say that again. Sulfuric acid is 1 trillion times stronger as an acid than acetic acid is down here, right? So you can see why we have to do this thing where we take the negative log of the pKa of the Ka to get the pKa, because if we didn't, we'd be dealing with these really huge numbers, right? And it's really difficult to deal with those kinds of numbers. My calculator screen doesn't show that many numbers, right? Again, a plug for Wiley Plus. You can't see what it says here, but practice Skill Builder 3.2 for using pKa values. Oh, this is just another the continuation of the chart right here, right? We have some more compounds, and these are the more basic compounds, because as we go down, right, the chart, the higher you are on the chart, the stronger you are an acid, right? But the weak you are as a base. But then when you start from the bottom and go up, then the weaker you are of an acid. The weaker you are as an acid, and the stronger you are as a base, right? So remember then that really large numbers mean a very, very strong base, right? Your ability to pull off a proton, right? To take a proton from something, okay? From an acid. So, again, skill builder, 3.3, using pK values, plug in the Wiley Plus there, make sure you sign on to the Wiley Plus. I've noticed that not all of you have signed on to Wiley Plus yet, and I need you to do that. Sign on to Wiley Plus. Only like half of you have. Wiley Plus is incredibly helpful. Make sure you sign on to Wiley Plus. I'll be checking. Next, we can actually use pK values to predict equilibria. And what that means is that we can use pK values to predict how much of reaction will make products, or will it stay more as reactants, right? So with the relevant pK values, you can predict which direction an acid-base equilibrium will favor, which is exactly what I just said, but in more chemical terms, right? Higher pKa's means weaker acids, which we already said that from the chart, right? So let's take a look at here. We have a base, right? A tert butoxide again, okay? And we have an acid here, which is water. Water is going to be acting as an acid. Water's pKa, not the hydronium ion, but the water's pKa is 15, okay? So 15 means 15.7, which means it's actually even weaker than acetic acid as an acid, which makes sense, right? If water were super acidic, we'd be all dead, since we're made of 75% water, right? So, think about that. Comparing that to the other side of the reaction, right, where the conjugate acid is the tert butoxide right here with a pKa of 18, right? And then the conjugate base is what? A hydroxide ion. Okay? The conjugate base is a hydroxide ion. Remember that equilibrium always favors the weaker acid and the weaker base, right? So, what does that mean? We have the weaker acid over here, pKa of 18. So most of the products, right, will be the tert butoxide and hydroxide ion. And that's what that arrow means. I don't know if you knew that, right? Let me clear that for you real quick so you see this. Whenever an arrow is bigger at the top, reaction arrows is bigger at the top, bigger going towards one side and smaller going towards the other side. The bigger side indicates, the bigger arrow indicates the more the products, right? So, or if it's smaller going to the left side, then it indicates more reactants are being made. So reaction here, in this reaction here, the equilibrium shifts such that mostly products are being made, and we're not going in the reverse reaction to make much of the reactants, right? If you had a reaction arrow that was like this, where the arrows on the top and the bottom going towards the left and the right of the reaction were the same, then what that is that there's the products are being produced at an equal rate as the reactants are being produced in the forward and the reverse reaction, right? Okay, makes sense. So, moral of the story of this particular slide, right? The side with the larger pKa wins and gets more products, okay? But it gets a little bit more complicated, so let's keep on going. Oh, I guess I have to go. I'm going to explain this again for you, but now in words that are actually here. Okay, so again, we have... Oh, no, this is a different one. I apologize. Yeah, it's a different one. It's not the tert butoxide. So in this case, right, we have a base here, which is literally a 1, 2, 3, 4, a butane carbocation. A butane carb anion, right? And I'll tell you now that this guy here does not like being without a proton, okay? It really does not like being without a proton. And so even though water is not a very strong acid, this butane's carb anion here will steal that proton from the water, making the hydroxide conjugate base, right? And making him the conjugate acid with a pKa of 50. And so let's do something here. Let's subtract the pKa values. 50 minus 15 gives you 34. And what that tells you is that there will be 10 to the 34 times more products than reactants. Which supports what I was saying just a second ago about how, man, this carb anion butane right here, it really does not like being without that proton. So it's gonna be making mostly that, right? But so again, moral of the story is that there really isn't much of an equilibrium here. It's more like an irreversible reaction, which means the reaction only goes to the left. Only goes to the right, toward the products. There's no reverse reaction going backwards, right? And that's because this guy is so basic. Like, it really wants to pull that proton off, right? Really wants to pull that proton off. Look at that conjugate acid. Look at that 50. Man, that's a really strong base. Or its conjugate base. Its base version is very strong. That's what I'm saying, right? Meaning that as an acid, it really doesn't want to get rid of this proton. It's going to keep it on there, right? Very, very weak acid. Scale builder, 30.4. Using pKa values again on Wiley Plus. So let's qualify acids now, right? So before we were using pKa values as a quantitative way of analyzing how strong an acid was or how weak an acid was. Well, now we can do it with qualitative methods, not quantitative methods, right? To determine the relative strength of two acids without knowing their pKa's, we compare the stabilities of their conjugate bases, right? The stabilities of their conjugate bases, which makes sense because the more stable a conjugate base is, the more likely that conjugate base wants to remain the way it is and not take back that proton, right? So the stronger the acid, the more stable its conjugate base. When an acid loses a proton, it forms a conjugate base, like we said before, which has a lone pair that is resulted from the loss of the proton, like we said before, right? To determine the stability of the conjugate base, we are actually looking at the stability of that lone pair that's on that conjugate base. Okay. So there's an acronym that we use called ARIO, and that stands for atom, resonance, induction, and orbital. Right? Those are the things that we look at, right, when we want to analyze the stability of the lone pair and that conjugate base, right? ARIO, that sounds familiar. ARIO, isn't that bad guy from Twilight? The bad guy, the Valtori guy. Like, he can touch people and see their thoughts or something. I think is that Aria? I could be wrong. Oh man, my girlfriend loves Twilight, so if I get that wrong, I'll be in a lot of trouble. Comment below and let me know if I'm in the YouTube video. If you're watching this on YouTube, let me know if I'm right. If Aria actually is the the bad guy on Twilight. Anyway, so we're going to take a look at each of these individually, of course. But the type of atom that carries the charge, right, is important. In evaluating the stability of that anion or that lone pair of electrons. Resonance, of course. Why? Because resonance is always what? It's always stabilizing species, right? And then induction. What induction is, just briefly, is the action of a electron withdrawing group that will pull electron density away from another area of a molecule. And then, last but not least, the orbital for which that those lone pairs resides, right? Oh, good old Oreo. Oreo. So, let's talk about the first one first. Atom, right? The A in Oreo is atom, okay? And we'll compare the butane to the propanol, right? Let's compare butane to propanol. We need to draw and analyze the stability of the negative charge on the conjugate bases, okay? So if butane loses this proton to something, right, to a base, we'll just go ahead and do that generic B thing, right, for base, like so. This bond here goes to that carbon there, right, and that's how you end up with this carbanion down here. If we do the same thing with some generic base here, pull off that proton there, that bond goes to the oxygen there, right? And then you get the oxyanion on the propanol, right? That's how you get those structures, right? Before we go to the next slide, which one do you think is more stable, right? Well, let's think about this here, right? Does a carbon like electrons more, or does an oxygen like electrons more, right? Let's go to the next slide, see what happens. So here we can determine whether an oxygen or carbon will be better at stabilizing a negative charge. Well, we already know that oxygen is way more electronegative, so it likes electrons, so it's going to be more stable because it's way better at stabilizing a negative charge. Way more stable than stabilizing a negative charge with a carbon, because carbons don't like electrons as much as oxygens do, right? So, moral of this story is the more electronegative an atom is, the better it will be at stabilizing a negative charge, right? I guess an important thing to note too is that size can actually stabilize a negative charge too. So as you go down the rows of the periodic table, an atom gets bigger, right? And so the bigger the atom you can stabilize, the more likely it will be able to stabilize a negative charge. But oxygen and carbon are on the same row. So electronegativity gives way to size when you're almost basically the same size when you're on the same row. So what that means then, okay, so sorry, here we go. I got a text message, I had to check it real quick. Anyway, so like we were just saying, right, that carbanion is way more unstable compared to the oxyanion, right, from the propanol, right? So the more stable thing is there. What that means then is that the propanol is far more acidic than the butane, right? The butane is more stable if it holds on to that proton, okay? And so the propanol, losing that proton there, it can still be stable because the oxygen loves electrons. It can stabilize a negative charge, right? And so that's why it's more acidic. That's why propanol is way more acidic than butane. That says more acidic, by the way. My head's blocking that. That says more acidic. Okay? So that's that's A in REO, atom, right? What atom is the lone pair attached to, right? The more electronegative that atom is, the more likely it is to be stabilizing that negative charge, okay? Absent a significant size difference in those atoms, okay? The R in REO, right, stands for resonance, of course. And what this means is that if it's a resonance stabilized structure, right, where that lone pair is, then it will be more stable. Okay, it will be more likely to be acidic. Which makes sense because we were talking about just in the last lecture how resonance stabilizes, delocalization stabilizes a species, stabilizes a molecule, right? So here we use ethanol as our example, right? And we use acetic acid in our other example, right? Let's see if we can predict before we get to the next slide which one is more acidic, okay? So my generic base comes off. Not comes off, but pulls off a proton. And then I get that, right? The electrons from that bond go into the oxygen, and I get an ethoxide. I think I overdrew that here. There we go. Ethoxide. Let me just draw that again because it got a little confusing, even for me. So my generic base comes in, pulls off the proton, breaks that bond, the electrons go to the oxygen, and I get an ethoxide, which looks like this. Okay. And then my generic base comes in, pulls off that proton right there. This bond breaks, and the electrons go to that oxygen right there. Right? And I get an acetate ion. Uh-oh. Right? If we just follow rule 1, the A in ario, right? It's about the atom it's attached to, the lone pair. But holy mother, the lone pair is attached to the same one, same atom this time, oxygen, right? So what do we do now? We go to the next one, the R in ario. Okay? Is this guy resonance stabilized? I don't see any patterns of recognition there for delocalization and resonance there, right? Right? Not really. But what is quite easily delocalized, right, is this guy right here on the acetate. That negative charge can go down there, forming a double bond, pushing the electrons from the double bond of the carbonyl into the oxygen, giving you this resonance structure. Right, giving you that resonance structure right there. So which one do you think is more stabilized? And which one do you think is a stronger acid? Well, this one is, right? Because it can be resonance stabilized, and it's a stronger acid. Let's see if we're right. Look at that, right? See, the charge here is localized on that oxygen of the ethoxide, right? Versus the charge is delocalized here on the acetate ion, right? So that means that the acetate ion is absolutely more stable, which means acetic acid, right here, right, that says acetic acid, is way more acidic than ethanol. Okay? Practice with Skill Builder 3.6, okay, on a Wiley Plus. Good times on that Wiley Plus. Now let's talk about the I in ario, which stands for induction, right? Now remember what I said what induction was, right? Induction is having electron withdrawing substituents, on the molecule with that will draw electron density from one side of the molecule to another. Okay. So let's compare them again, acetic acid now, with trichloroacetic acid, right? Oh no. We've already done rule 1 here, right? Because if the base comes over, my generic base comes over and pulls off the proton, leaving my negative oxygen right there, right? And then the base comes over, pulls off the thing, leaving my negative oxygen there too. The negatively charged oxygen that is got the lone pair is on the same oxygen, same atom, right? They're both oxygens. So the A in ario doesn't apply. So what about the R in ario for resonance? Well, holy crap, that doesn't apply either. Because with this proton pulled off and the oxyanion here with the negative charge, and the anion here with that negative charge too, right? They have both the same resonance structures, right? Look, watch. I'll just draw this again so it's a little bit of resonance practice, right? I'll have this guy to begin with, right? After the base pulls off the proton, comes down, makes a double bond there, breaks this single bond, and then the electrons go up to the oxygen. And I get the oxyanion up there. And then the carbonyl down there now. Well, let's try to draw the resonance structure for this guy then. I have 3 chlorines. Right? And then it's attached to the carbonyl of the carboxylic acid. And then the base took off the proton, so I'm left with the oxyanion with its lone pair right there. And I'll draw the resonance structure double bond forms, double bond breaks, and now I'm left with 3 chlorines. Right? The oxyanion at the top, and the double bond at the bottom. That's actually where the resonance structures end. Right? Because the chlorines are attached to that carbon right there using sigma bonds. Right? Not, sigma bonds, which are sp3 hybridized. They are not a part of the conduit of p orbitals. Okay? So there's no, those electrons are not going back and forth on the chlorine. Okay? So the resonance structure that is achieved from the carboxylate side of from the molecule is the exact same. So the R in REO doesn't apply, right? So what's left? Now we have the I in REO, which is induction. And we all know that chlorines are electronegative groups, right? They're far on the right side top of the periodic table, right? So they're super electronegative. And so the inductive effect, right, it can stabilize a formal negative charge by spreading it out. And how does it do that? It withdraws electron density away from it, right? It draws electron density away from it, okay? And that stabilizes the negative charge. Which means then trichloroacetic acid is actually more acidic than acetic acid is, right? Good stuff, good stuff. Here's some more examples right here, or not some more examples, but some real data to show you that the I in REO is real, right? We have here acetic acid, its pKa is around 5, right? But we add a chlorine to that methyl group at the end there, an electron withdrawn group that is capable of induction. And what do we get? A pKa of 2.8. So it's gone down. That means it's a stronger acid now, right? We'll add 2 chlorines there, pKa of 1.25, even stronger because it's got 2 electron withdrawing groups capable of induction. And then, if you bring it to 3, the trichloroacetic acid that we just saw on the previous slide, right? pKa is close to 0, right? 0.7. Right? So it's even stronger now. Again, practice with Skill Builder 3.7 on Wiley Plus. And then last but not least, we have the O, which stands for orbital. The orbital of REO, right? And this is actually quite self-explanatory. Like you can really see it, right? Because what it says is that the closer electrons are held to the nucleus, the more stable they are, right? So the shorter the atomic orbital, the closer it is to the nucleus. So you have an sp, right? And you have an sp2 and an sp3, right? They all have different lengths to the nucleus, right? And the closer you are to the nucleus, the more stabilized you are. Let's take a look at that. Here's REO and the orbital in REO. Let's consider the relative stability of the H's, or the protons, are indicated below. This proton here and this proton here, right? This proton here is attached to an sp2 carbon. This proton here is attached to an sp carbon. There we go. And you recall from the last was it the last one, or maybe it was the one before that lecture, where we learned that sp orbitals are shorter than sp2 orbitals, which are shorter than sp3 orbitals. So the one that holds the proton the closest to the nucleus is what? The sp orbitals, right? So when we take a look at this, and a base comes over, right, and pulls off a proton here. A base comes over and pulls off a proton there. And then we go down and get a negative charge on the double bonded carbon there. And we get a negative charge on the triple bonded carbon there, right? Which one do you think is more stable, right? This guy here or this guy, right? This guy here or this guy? Well, the one that's the sp3 hybridized, or sorry, sp2 hybridized, would be the more, well, let me say that again. The one that's the sp hybridized The one that's sp hybridized is the one that's going to be more stable, right? This carbon ion is going to be more stable because it's being held. Those electrons are being held closer to the nucleus, right? Which means then this proton is way more acidic. Let's see if we're right. Look at that. The lone pair in the sp2 orbital not as close to the nucleus, so it's less stable. And I just wrote all over that, so you can even read that. So let me move that. There we go. Right? Whereas the lone pair in the sp orbital is closer to the nucleus and then more stable, which means that this alkynic proton, right, instead of this alkenic proton, I made those up just now, but the alkyne means triple bond, alkene means double bond, remember? The one with the triple bond is way more acidic. Okay, way more acidic. So now let's take a look at the numbers. We have ethane here, right? And there's a single sigma bond right there between the two carbons, right? These protons are all, they can be acidic, right? But look at the pKa with the sigma bond there, right? The single sigma bond, it's 50. Jesus. It's not very acidic at all, right? It'd rather be like that than lose its proton. Then we take a look at ethylene, pKa of 44, which makes sense because it's got a double bond right there. And then the acetylene with the triple bond there, or the sp hybridized carbon there, right? Man, pKa of 25, way stronger than the rest, right? The lower the number, the stronger the acid. Again, practice with Skill Builder 3.8 on Wiley Plus. So, when we assess the acidity of protons, we generally can use REO as an order of importance for stabilizing effects. We start with the atom, the A in REO, the R in resonance for REO, I in REO for induction, and the O for orbital, right? But the problem is that it's not 100% reliable. There are some exceptions, right? There are some exceptions. And I think we're going to go through those now. Okay. So ethanol is more acidic than polypropylene. Okay. Therefore, the conjugate base of ethanol must be more stable, right? Must be more stable. Ethanol has a pKa of 16. Propylene has a pKa of 43. So yeah, it is more acidic, right? But it turns out that, and then ethanol is more stable, right? And then the polypropylene conjugate base, which I don't know what we call that, the polypropylene anion, right? Right, is less stable, right? So when we use REO to do that kind of like analysis, it actually works out. It actually works out. Okay? It makes sense. But then, here's a case where it fails. We have here a pKa of 25 for the acetylene, right? And then we have here a pKa of 38 because for the ammonia, right? And when we use REO, right? When we use REO, nitrogen here is actually the more stable, the more electronegative atom, right? And it's stabilizing the lone pair up there, right? It's stabilizing the negative charge anion lone pair up there, right? Based on REO. But for some reason, the pKa of ammonia is so high, which suggests then that the reaction proceeds mostly towards that direction, meaning that the products are going to be this acetylene ion, anion, right? Carb anion, and the ammonia, right? So what that means then is that this actually fails our REO test, right? It doesn't work. And sometimes all you really need to know is the pKa. And that doesn't say that there. Let me move my head out the way so you can see. And sometimes all you need to know is the pKa of the reaction, right? Because those pKa, the pKa's of each of the species are going to be exceptions to the REO priority rule, right? The pKa will be the exception to the REO priority rule. And you're going to see this a lot in organic chemistry too, where we go through and we say these rules, right, that you can use most of the time, but there's always going to be some exceptions. And in this case, we would think based on REO, right, because the A in atom says that the more electronegative atom can stabilize, is more stabilizing of the negative charge, right? We would think that the nitrogen would be what was more stabilizing there in the anionic amine right there, right? But turns out though, the pKa outweighs the importance of REO, and ammonia here has the higher pKa, which means that it's much more likely to stay as ammonia than be this anionic form. And so the species that are going to be produced most often here, right, are going to be the anionic, the acetylene carb anion and the ammonia, right? So sometimes you just pKa is all that matters, because it is the exception to the REO priority rule. So this next slide just goes through and repeats or just summarizes what I just said. Let me bring myself back, because I like seeing myself in the presentation, right? You can predict the equilibrium of the reaction, right, based on the pKa values, right? In this generic, for example, acid-base reaction, right, where the base comes over, pulls off the proton, the A goes there, right, and now the negative charge goes to the A, and now you have the conjugate base and the conjugate acid, right? But just remember that the higher pKa will always be favored, right? The species with the higher pKa will always be the one that the reaction goes towards the most. So you can practice this with using Wiley Plus again. Wiley Plus Skill Builder 3.11, predicting positions of equilibrium, right? That Wiley Plus, man, that's an invaluable resource. Make sure you're using it. Okay, make sure you're using it. Now that we know how to predict the equilibrium position of these acid-base reactions, let's learn how to actually choose an appropriate reagent, acid, for an acid-base reaction, right? So for these examples below, they want you to use table 3.1 to choose a reagent that would effectively protonate each of the following molecules, right? So an acid that would effectively protonate each of the following molecules. I don't really want to jump back all the way to the beginning of the lecture presentation, so we'll just use some approximate numbers here. We have an acetylene right here, the first one. And acetylene has an approximate pKa of about, I'd say about 25, I think. Okay? Well, that means it's a super strong base, right? It's a super strong base. What's the highest on the chart? I think the highest was like 50. So it's pretty strong. I mean, the anion here, or the carb anion here, would much rather be protonated than not. So basically, any acid on that chart that has a pKa of lower than 25 would be able to protonate that acetylene, right? It would be easily able to just eat up that proton right there, leaving behind a conjugate base, right? Same is true of this over here. This is actually an acetone ion, right? An acetone anion, or an acetone with a carb anion on it, right? And again, I mean, these methyl groups right here, right? They need their protons. They love their protons. I think this guy has an approximate pKa of about 19, right? So again, much rather have a proton than not. So any old acid that has a lower pKa than 19, you can just go and rip that proton right off of there, right? Go and rip that proton right off there, making you some acetone so you can, remove your nail polish, right? The next one here, that's actually the acetate ion, right? Which comes from acetic acid, right? Which looks like this, right? and then an acid and a base comes over, rather, and pulls off that proton and leaves you with that, right? So that's acetic acid over here. Okay, and it leaves you with this acetate ion. So the pKa of the acetate ion or acetic acid is approximately 4 to 5, I would say. Okay, approximately 4 to 5. So that's actually relative to the rest of the chart, right? It's pretty up there as far as acids go, but it's still not a very strong acid, right? Not a very strong acid at all. So acids that are stronger than it would be able to protonate it. Things like, for example, the hydronium ion, which looks like this. It has a pKa around -2, right? So it can definitely, that as acting as an acid, can definitely protonate an acetate ion, right? And things that are even stronger than that are on the chart too. For example, sulfuric acid, H2SO4. We'll see a structure for it later, so I'm not going to draw it out here. But it's got a pKa of approximately -9, right? So that's super strong. That's definitely going to protonate the acetate. And then maybe also, not maybe also, but absolutely, HCl, hydrochloric acid, which has a pK of around -7. So all those acids that are stronger than acetate, right, which means they have a pKa number lower than 4 to 5, they're going to be capable of protonating acetate, making acetic acid. And honestly, too, acetic acid, when it's in water, it'd much rather have that proton on there anyway, right? It'd much rather have that proton on there. Excuse me. Now we actually have an acetone, right? We actually have an acetone. And the thing that's going to get protonated here is going to be the oxygen at the top right there, right? Those lone pairs are going to come over and pull off an acid from somewhere, or a proton from somewhere. From a strong acid, right? Pull off a proton from a strong acid. And so it's got a pKa actually of the form that is acidic, which is this. All right, the form that's acidic, which is that, has a pKa of about -7. So it's actually really close to hydrochloric acid's pKa, right? So what that means then is about the only thing that can protonate this guy is sulfuric acid, H2SO4, right, with its pKa at approximately -9, right? So yeah. If you get rid of all that stuff right there, where I was trying to show, the electrons trying to pull off that proton, this is the acidic version, and its pKa is down in the -9s. I mean -7s. I mean, what that means then is that oxygen rather not be protonated, right? So you're gonna have to have a strong acid to protonate that thing, strong like sulfuric acid, right? So that takes us to talking about leveling effects, right? What are leveling effects? Well, leveling effects are effects that are introduced when you have a solvent that you use for the reaction that also interacts with reactants, right? When you're doing a reaction, you want a solvent that can surround the reactant molecules but not actually interact with it, because you want those reactant molecules reacting with each other, not reacting with the solvent, right? And so there's some rules here that are that help you determine if a solvent is appropriate for an acid-base reaction. And they're based all around water. Water can act as an acid or a base, which we saw that already before, right? It can it can receive a proton as a base, become the hydronium ion, and then the hydronium ion can actually protonate things, right? So it can be an acid or a base. And since it can do that, it can be a leveling effect. It has a leveling effect on strong acids and bases. All right. So acids stronger than the H3O cannot be used in water, and bases stronger than hydroxide, right, which is the base form of water. When you pull off one of its protons, hydroxide cannot be used in water. That kind of makes sense, but let's see why. So here we have the example of the acetate ion again here. Right? And water is actually the acid in this case. Oh, I wrote that wrong. Let me erase that and do that again. We have the acetate ion, right? And we have water. And water is the acid here. How do we know water is acting as the acid? Because the electrons from the acetate ion's oxyanion are coming over here to take that hydrogen, that proton, away from the water. And then the water, those electrons from that bond go to the oxygen, forming the hydroxide ion, right? So you're comparing then, right? You're comparing then the strength of the base as it's compared to water, right? So appropriate use of water for a solvent when base is not stronger than hydroxide. So the base here is the acetate ion, right? And the acetate ion's pKa is 4.75. I was pretty close. I said it was around 4 to 5, right? But the pKa of water, right, acting as a base here, right, is 15.7. What does that mean then? That means then water is a much stronger base than, hydroxide / water is a much stronger base than acetate is, right? Hydroxide is a way stronger base than acetate is. So that means then that for the acetate ion, water is in fact an appropriate solvent, right? Water is only not an appropriate solvent when the base is stronger than hydroxide, which makes sense because then the hydroxide is going to be interacting with the reactants more than the water will be reacting with the reactants more than it will be reacting with the reactant. The solvent will be reacting with the reactants more than the reactants will be reacting with each other. Tongue twister. Sorry about that. Okay. So acids that are stronger than H2O can't be used in water, right? So we were just talking about bases. Now let's talk about the acids. So for example, water would react with sulfuric acid producing H3O here, right? So here we go. In this time, water is the base, okay? And as the base, its electrons and oxygens come over here, pull off the proton from sulfuric acid, leaving behind, right, that broken bond with the electrons from that bond going to oxygen, leaving behind the sulfate ion, SO4, right? The hydronium pKa is negative 1.7, and then the pKa of sulfuric acid is negative 9. So which one is stronger? Obviously the sulfuric acid is stronger, right? And since it's stronger, most of what you have is going to be the sulfate ion, right, left in solution if you do this. And what if you need the sulfate ion as a reactant? I mean, not the sulfate ion. What if you need the sulfuric acid as a reactant? Well, there won't be any in there left if you're using water as a solvent because the water's taking that proton because it's a base, leaving behind only the sulfate, right? So virtually no sulfuric acid would remain if we wanted it to be available to react with another reagent, right? If you used water as a solvent. Okay? Here's another example, another base example actually, an example in which a base, water would not be an appropriate base. Okay? So we have here an anionic amine, right? Anionic amine, right there. Okay. And it turns out that this anionic amine, I think it has like a pK around 38 or something like that, right? Dang, that's a strong base. What was Waters again? Like 15, 14, something like that, right? So, obviously, in this case, since this base is stronger than hydroxide as a base, you can't use water as a solvent, right? You can't use water as a solvent. Why? Because this thing will rip off a proton off of water, like that, rip off a proton off of water, making the amine before it would react to pull off the proton off the alkyne, right? So, just some more, I guess, exceptions to REO again. You know, REO is good in general, right? And you can use that for most applications, but sometimes, you know, it doesn't work out too well. So, for example, REO cannot be used to explain the pK difference between tert-butyl and ethanol. And you know, part of the reason why is because they're so similar, right? Like if you try to use REO, you know, the atom that it's attached to, right? The resonance that is there, right? The induction effects, right? And then the orbitals, all that stuff is virtually the same between tert-butyl and ethanol, right? But so how does it have different pKa's then? Well, let's take a gander at some stuff. It turns out that sterics, right, and solvating effects also affect the pKa, right? And what does sterics mean? Well, sterics is something we'll get into a lot in the next few chapters, but basically, it's how much of the three-dimensional structure of an atom hinders things around it, right? Like it has, it takes up so much space that it doesn't want to be around it, so it's like it's sterically hindered, right, because of its shape. Okay. So when you take a look at tert-butyl, not tert-butyl, sorry, tert-butoxide, right? After it's lost its proton and become a base, right? A conjugate base. You take a look at tertiary butoxide or tert-butoxide, right? You have solvent molecules surrounding the oxygen, right? Forming an ion dipole interaction with the oxygen. But you also have the same thing happening over here with the ethoxide, right? But notice that you actually have more solvent molecules surrounding the oxyanion on the ethoxide, right? And that's because it's a straight chain carbon chain as compared to this branch chain that's on tert-butoxide. These three methyl groups right here, right, which you can see inside that electron cloud right there, right, actually sterically hinder and block solvent molecules from surrounding the oxyanion, right? Surrounding the oxyanion. So they don't do as well a job as it doesn't do a good a job. It doesn't do as well of a job at stabilizing, right, the negative charge. Whereas over here, ethoxide doesn't have all those methyl groups, you know, branching out and blocking the solvent molecules. So you have more solvent molecules that can surround the oxyanion, right? And with the more solvent molecules around it stabilizing the oxyanion, it makes it so that it's a stronger acid, right? And that's why you have a pKa of 16 here for ethoxide, but a pKa of 18 here for tert-butoxide, right? So solvent effects also, in addition to REO, help with the determination of the stability of the conjugate base, right? And so that's how we answer that question. Why is it that terbutanol and ethanol have different pKa's, virtually the same REOs, right? Well, it's because when you look at it three-dimensionally, the solvent can't surround it as much on butoxide, tert-butoxide, as it can on ethoxide because of the branch methyls on the tert-butoxide, right? Excuse me. So, in acid-base reactions, we also have counter ions too. Counter ions are ions that are they're kind of like spectator ions that are in the GenChem, sections, right? They're there so that it can balance out charge, right? But we don't usually include them in organic reactions. So in this case, right here, we have sodium, right? And that's a spectator ion. We're calling them counter ions here, right? And we don't usually include them in our reactions, right? So that brings us to the very end of our acid-base lecture, right? And we ended with talking about the third acid-base theory. Recall, the first acid-base theory was Arrhenius, where an acid donates a proton to solution, and then a base donates a hydroxide, right? But the problem with the Arrhenius acid-base theory was that it was very confining. You identified an acid and a base just because one had a proton and the other had just hydroxide. But we just saw in the previous example that a super strong base, sodium hydride, actually was stronger base than hydroxide was, right? But it doesn't apply. You can't use Arrhenius acid-base theory, right, to explain that. So then we came up with the Bronsted-Lowry acid-base theory, right, BLAPT, where an acid still donates a proton, but in this case, a base receives a proton or is a proton acceptor, right? Which actually does help in explaining and describing what happens with sodium hydride, right? Because it's receiving a proton, right, from water, right? So that makes sense as a base, right? But again, now you're stuck just talking about protons. But what if you're in like an aprotic solvent, right? Or you're using reactants that don't even have protons, right? So now we have to expand it even more. And the way we do that is with Lewis acid-base theory. And in Lewis acid-base theory, an acid actually accepts a pair of electrons, right? Whereas a base donates a pair of electrons. Wow, this just expands this to every single reaction there is in chemistry. Because what is a reaction? A reaction is the movement of electrons, right? To form new bonds, break old bonds, whatever. That's what a reaction is. It's the movement of electrons. So now you can describe any reactant as an acid or a base. A Lewis acid or a base, based on its electron movement, right? Acids under Bronsted-Lowry definition are also acids under the Lewis definition. It's exactly the same, right? Because as a Lewis acid accepts a pair of electrons, right? It's accepting that pair of electrons, right? When it loses its proton, right? When it loses its proton, because that proton goes to the base and leaves behind that bond, right? And then it accepts protons, right? And then bases under the Bronsted-Lowry definition are also Lewis bases too, because those bases are what? They're donating a pair of electrons to the base. To the acid, right? When they pull off the proton. Okay? So here's a really good example here. We have water. It's acting as the base. The base, pulling off that proton, right? So this is the Lewis base. The hydrochloric acid is the Lewis acid. Right? And notice that now the Lewis base at the end, what did it do? It donated a pair of electrons, right, to this proton here, right? And that's why it's got a positive charge now. Right? Then if you look at over here, the chloride ion, right? It received or accepted a pair of electrons, right? Because it got it from the bond that was broken between the hydrogen and it when the water took the proton. And that's why it's got a negative charge now, right? There you go. So quite literally, Lewis acid-base theory can describe every reaction in chemistry. Because again, reactions in chemistry deal with what? Electrons, right? Acid-base reactions are, protons, right? But every reaction, including acid-base reactions, involve electrons, the movement of electrons. So, check this out, right? This is just a quick review, right? A Lewis acid accepts and shares a pair of electrons. A Lewis base donates and shares a pair of electrons, right? We just saw that in the previous reaction with hydrochloric acid and water, applying it to a Bronson-Lowry acid and base, right? Here, we notice that we do have some Lewis acid-base reactions that cannot be classified using the Bronson-Lowry definition because they don't involve protons. Right? They don't involve protons. So let's take a look at this. We've got water and we've got boron We've got water and we've got boron trifluoride here, right? Again, water here is the Lewis base. It's going to come over and donate some electrons to boron, right? And when it does that, boron now has a negative charge, right? And so that's why boron is the Lewis acid. It received electrons, getting the negative charge, right? The oxygen lost electrons. That's why it's got the positive charge, right? Because they're both now sharing it. Right? And you can't classify this as a Bronson-Lowry reaction at all because no proton transfer was involved. It was only electron transfer. Does that make sense? Practice this skill with Skill Builder 3.13, identifying Lewis acids and bases, in Wiley Plus. Interesting stuff. That actually ends today's lecture. And there is no quiz assigned for today's lecture, but there will be one tomorrow. That being said, the acid-base assignment is assigned and due by tomorrow at 7:59 a.m. That's on June 8th, 2021, right? And that assignment is due because we finished the entire chapter on acid-base theory. Right? And just know that we will be using Lewis acid-base theory for the rest of the semester. Okay? Again, I just wanted to remind you that at the time of this recording, people are still taking the exam, and so I won't be able to say anything about it just yet. But once everybody's taken the exam and the exam is graded, I've decided that I'm going to go over the entire exam and the quizzes for you in a separate video. And because I think that would be very helpful for you in studying for the final exam. All right, I guess I'll see you again tomorrow then for no exam tomorrow. Sorry, for the next lecture. I believe it's lecture 5, and then also lab will be tomorrow as well too. So don't forget about that. Have a good day.